Hello everyone. Let me introduce myself and my group mates. My name is Zhumagul Orynbassar and my group mates are Nurzhan Seitmaganbetov and Alikhan Kurmankulov, and our supervisor is Nadera Bulai. The topic of our presentation, which I would like to present, is Introduction to Nuclear Logs. And this presentation consists of several parts. First of all, I will talk about nuclear logging and how it works. Then I will give you information about history, nuclear radiation transport, types of nuclear logs, its problems, its applications and developments. And finally, I will discuss about nuclear measurements and statistics. Okay. Nuclear logging has been used in some form since the late 1920s to provide information on lithology and rock characteristics. Continued technological advances have provided improved methods for analyzing the measurements of natural and induced nuclear readings. Even with the better tool designs, the long-standing problem remains that logging tools do not directly measure the formation properties that engineers, geologists, and petrophysicists need to describe a reservoir. The goal of log analysis is to map out the downhole values of reservoir characteristics chiefly as porosity, fluid saturations, and permeability. Unfortunately, nuclear logging tools only measure gamma ray or neutron count rates at cleverly positioned detectors. Nuclear log interpretation rests on smart processing of these tool readings. Understanding what the tools really measure is the key to better log analysis. This presentation gives an overview of nuclear logging and how they measure the transport of radiation. Let's define how it works. Nuclear logs work because gamma rays and neutrons are penetrating radiation. Unlike visible light, they can traverse tool housings and boreholes and still sample a significant volume of the formation. They also respond to different properties than resistivity logs, which measure the conductivity of a formation. History of nuclear logging. The first practical oil well logging system based on a nuclear process was developed during the period 1935 to 1939 by Howell and Frosch. Using Geiger counters, they demonstrated that variation in the intensity of gamma rays produced in a borehole due to the decay of the naturally occurring radiative elements in the surrounding rocks could be measured in both open and cased holes. As a result of this work, the natural gamma ray log was introduced as a commercial oil field service in 1940. And the next slide about nuclear radiation transport. Nuclear logs are based on the interaction of nuclear radiation with metamaterials like sand, clay, water, and hydrocarbons that together make up a reservoir. For logging, the interactions are primarily particle scattering interactions. Even though gamma rays are usually discussed as electromagnetic radiation, for nuclear logging they are treated as photons, classical particles. And well logs exploit only two types of nuclear radiation. It is gamma rays and neutrons. Depending on the type of energy of the particle, different scattering processes predominate, and a beam of particles impinging on a slab of formation from the left to the right. Next slide is about nuclear logging types. The main nuclear logging types is the gamma ray logs, neutron logs, nuclear logging while drilling, carbon accident logs, and geochemical logs. First of all, I would like to present you the gamma ray logs. The main gamma ray logs is the spectral gamma ray logs and density logging. Spectral gamma ray logs is the latest variant on the gamma ray log. This starts out exactly the same as the standard gross gamma ray count log. Gamma rays from the formation are counted in a detector system. However, there is an added level of sophistication. The energy of the gamma ray captured by the detector is proportional to the brightness of the light pulse it produces. And this brightness in turn determines the size of the electrical pulse produced by the photomultiplier. By sorting the pulses from the photomultiplier into beams by their size, a spectrum equivalent to the energy spectrum of the incoming gamma rays is produced. The energy of gamma rays is determined by which element emitted them. Spectral natural gamma ray systems designed for potassium, uranium, thorium logging have been applied to evaluate simulations and compilations. The next type of gamma ray logs is density logging. Density logging is another application of gamma rays in gathering data about subsurface formations. Density logging tools rely on gamma scattering or on photoelectric absorption. The next type of nuclear logs is the neutron log. The main type of neutron logs is the neutron porosity logs and pulse neutron lifetime logs or PNL logs. Neutron porosity log first appeared in 1940. It consisted of an isotopic source, most often plutonium beryllium, and a single detector. Many variations were produced exploiting both thermal and epithermal neutrons. In most of the early tools, neutrons were not detected directly. Instead, the tools counted gamma rays emitted when hydrogen and chlorine capture thermal neutrons. The next type of neutron logs is the PNL logs. PNL logs measure the die-away time of a short-lived neutron pulse. They probe the formation with neutrons but detect gamma rays. The next type of nuclear logs is the nuclear logging while drilling. Nuclear logging while drilling is the main subset of measuring while drilling, and these measurements are relatively inexpensive, although they require a more sophisticated surface system than is needed for directional measurements. The basic measurements of nuclear logging while drilling is resistivity and density porosity. Log plotting requires a depth tracking system and additional surface computer hardware. The next type of nuclear logs is the carbon-oxygen logs. Carbon-oxygen logging was developed for fields with low salinity where a pulse neutron lifetime log is not useful. However, the nature of this tool limits both its applicability and confidence in the results. To obtain a lithology compensation, most carbon-oxygen tools also record neutron capture spectra in which elements such as calcium, silicon, and iron reveal themselves. Neutron capture only occurs shortly after the neutrons have slowed down to thermal energies. Buffer timing separates inelastic carbon-oxygen spectra from capture spectra. Experience with carbon-oxygen logging has been uneven at best. And the last type of nuclear logs is the geochemical logs. Geochemical logging is still struggling to find applications. Chambéry's latest incarnation is called the environmental capture sonde. Applications lie primarily in rock and clay typing for reservoir description. And the goal of this type of log is to add additional elemental concentration to the formation model. And let's talk about problems of nuclear logs. Reviewing the status of nuclear logging begins by examining the weakness of the current technology. They have only two problems. First problem, because a nuclear tool average over a shallow or bulk volume, the borehole can represent a major part of the tool's response. And second problem, even if all borehole effects can be removed, the fact remains that nuclear tools do not respond directly to petrophysical parameters. Let's talk about applications of nuclear logging tools. Consider some of the limitations of the current technology. Grouping nuclear logs according to the underlying nuclear physics highlights the blurry relationship between what they measure and what we expect from them. And the table on this slide summarizes such a classification scheme. The basic uses of the nuclear log were known when the method was introduced. Is the correlation, discrimination of gross lithological units, and perforating. And the main tool of nuclear log is the gamma ray. In physics, exploited is natural gamma rays. It reads gamma ray counts, gallium, uranium, thorium counts. And desired information of this tool is clay type and bedding, formation density, and porosity. And let's talk about developments of nuclear logging. In recent years, extensive effort has been devoted to developing new instruments and techniques which will aid in the determination of the chemical composition of formation rocks and fluids. Of particular interest to the exploration geologist is the possibility of measuring in situ the individual concentrations of uranium, thorium, and potassium in formation rocks. And our last slide about nuclear measurements and statistics. For logging purposes, all nuclear radiation behaves as particles, and all nuclear log measurements are particle counting experiments. There is randomness to the arrival of the particles, so accurate count rate measurements need to be very long-term averaged. As a result, fluctuations in radioactive logs may be statistical rather than the result of a real change in formation properties. Counting experiments obey Poisson statistics. A Poisson distribution characterizes such experiments. If the expected value of the number of counts received in a given period of time, then the probability of obtaining a particular number of counts on a given repetition of the experiment is given by the formula which called the Poisson distribution. The Poisson distributions capture how the statistical nature of nuclear counting measurements influences the precision of such measurements. That's all. It's our references. Thank you for your attention.